Welcome everyone. It's my great pleasure to introduce Anand Deo for this thesis defense. Although his thesis is of high quality and doesn't really need to be defended, it speaks for itself. But his thesis is on asymptotic study of risk in financial systems, algorithms, and analysis. I'll just say briefly about Anand before he makes his presentation. Anand joined TIFR in 2015. He was a topper from Mumbai University in electronics. He's done a great thesis here. What one likes about him was that just the enormous energy he brought into picking up difficult concepts, thinking them through, solving, coming up with intricate proofs. One got the impression working with him that, he never sleeps. He's always energetic, always working to, willing to dig himself into difficult problems. And also was a great help in teaching classes to students. So he did a lot of that as well in TIFR. So with that, it's it's a great pleasure to see him complete his PhD. It's come out to be as I mentioned earlier, a high quality thesis. So Anand, over to you.
Thank you for the introduction, Sandeep. So my thesis is going to be about the study of risk in financial systems. And it's based on joint work with Sandeep and Karthik. And before I start, I would like to thank both of them for their guidance over the last 3-4 years. And I would also like to say that without their help, this thesis would not have been possible. And I mean, it would not have come out as well as it has. So a bit about myself before I begin. Like Sandeep mentioned, I joined TIFR in August 2015, immediately after completing my undergraduate degree. And I did a master's project until January 2017, after which I commenced my PhD thesis, and which I submitted 6 months ago. And the talk which you're going to hear is based on 3 to 4 years of work which has gone into my thesis. Part 1 consists of a problem which we solve in the credit risk setting. So it concerns developing closed form parameter estimates. And this is joint work with Sandeep and has appeared in operations research this year. Part 2 concerns deriving accurate estimates of certain tail risk measures. And this is joint work with Karthik, which I've done at SUTD and while I was at TIFR as well. And parts of this has appeared in various conferences. So CDC last year, the winter simulation this year. And a large chunk of this we have submitted to operations research. So a major portion of this has been submitted to operations research just a couple of months ago. And the third part is again joint work with Sandeep, and that concerns deriving simplifications for large banking networks. And that has appeared in winter simulation conference a couple of years ago. Now, before so by the way, in terms of thesis chapters, the first part was chapter 2, the second one was chapters 4 and 5, and the third one was chapter 6. Now, before I get into the details of each of these parts, let me provide a very high-level outline into what we do to address each of these problems. The first problem, which was deriving closed form approximations to maximum likelihood estimation, concerns estimating default probabilities given certain economic data. So you've got you observed certain economic covariates, and you've got a financial firm, and you want to predict what is the probability that it defaults in the next month. And this is an important problem because this helps in sort of assessing riskiness of particular firms, in assigning credit ratings, and in sort of ranking firms in order of risk and so on, and has received significant attention over the past couple of decades. So here are some representative papers from from say 7 or 10 years back. This is a very interesting work which has come out very recently, and this sort of combines deep learning techniques with sort of these parameter estimation methods. By this, I want to sort of emphasize that this is a very active and interesting area of research. So I mean, it's interesting enough that in fact the National University of Singapore here has got a subsidiary which computes these default probabilities on a daily basis for 50 to 60,000 firms, for registered firms, or spread over say around 100 countries. So it is a very, very, very exciting area of work. And the way one typically calculates these default probabilities is one looks at historical financial data, and one fits a parametric model to this data. And that involves solving a rather complicated optimization problem, given especially the large amounts of data which one typically has. And solving this large optimization problem has sort of two drawbacks. One, because of the huge amounts of data, this is really slow, so it takes forever to solve it. And two, because it's sort of a very complicated operation mathematically, it fails to give any kind of structural insights into how these parameters depend on the data. So how the underlying parameters which you're estimating depend on the data. And our contribution is to alleviate these two difficulties in typical methods used to estimate these underlying parameters. We do this by deriving a closed form approximation to the maximum likelihood estimation method, which is typically used to solve these problems. And because our approximation is closed form, we'll be able to precisely identify on what factors, on what how these underlying parameters depend on the underlying economic data. And we will be able to do these computations almost instantly because of the closed form of our estimate. Part 2 of the thesis concerns tail risk estimation. And tail risk estimation is basically essential in order to analysis and estimation, actually, tail risk analysis and estimation. And that is basically essential in order to understand how rare but catastrophic events can affect a financial system. And again, this is a very widely studied area. So for example, financial risk management, there has been a lot of work on this. Portfolio optimization in power networks. And this is actually something which I was quite surprised to find when we started working on these problems a couple of years back. And more recently, people have started incorporating these kind of rare event analysis techniques into machine learning problems as well. And it's not only that we want to analyze how rare events occur, but one also often wishes to incorporate the occurrence of these tail events into decision making. So one wishes to sort of make decisions which are in some way sensitive to what happens in deep into the tails of certain stochastic losses. And what we do in this setup is we derive computationally and data efficient algorithms to estimate these tail risk events. I will come to what I mean by each of these terms in due course of time. So whenever I explain the particular topic in detail. The last part of the thesis concerns analysis of large banking networks. Now, typically in an economy, there are a large number of banks and they interact with each other. And what could happen is that a shock basically means a large loss to the assets of one particular very well-connected bank could sort of propagate through this system, and it could lead to a widespread kind of economic distress. And in order to analyze how these shocks kind of propagate through the system, one needs to understand how the structure of the system is. So understand the underlying structure of the banking network. And this is often a complicated task because these banking networks are rather hard to sort of, they're not very tractable because the connections are quite complicated. And what we do is we derive structural simplification. So as the banking network becomes large, we derive sort of limiting forms for how these banking networks look when they become large. And this we hope will provide structural insights into how these defaults kind of percolate through the network. So how distress kind of percolates through the network. So just to recap, the thesis consists of 3 parts. The first one is just in the first one we sort of derive these closed form parameter estimates. In the second, we analyze a variety of tail risk estimation problems, and we derive data and sample efficient algorithms to estimate these quantities. And in the third, we analyze large banking networks, and we derive sort of a limiting representation, and we derive a Monte Carlo algorithm to compute certain quantities dependent on this limiting representation. So with that, I will come to the first part of the talk, where we derive simple closed form maximum likelihood estimation. And like I mentioned, this is joint work with Sandeep, which has appeared in operations research this year. So if you recall, the objective here was to, given a set of economic covariates, estimate the probability that the firm defaults, say in the next month. And typically in this setting, these conditional default probabilities given covariates are modeled as certain parametric functions of the underlying economic factors. And here it is good to see an example so that it becomes clear what I mean by parametric functions. So for example, and this is something which is, so these are models which are used in practice. Given economic covariates Vi, the probability that a firm defaults in the next month may be modeled as e power beta transpose v minus alpha over 1 plus e power beta transpose v minus alpha. So this is a logistic sort of a model of default probabilities. And here, sort of estimating default probabilities accurately amounts to estimating these parameters beta and alpha from data. And before I sort of get into how we do the parameter estimation, let me kind of explain what these covariates actually are. So by economic covariates, I mean two types of covariates. One are macroeconomic factors which affect all the firms which live in the economy, and these include GDP and inflation and S&P 500 returns, for example. And so these affect all the firms in the economy. And there are certain firm specific factors in addition to these macroeconomic factors which are indicative of a particular firm's health. So these include assets to liabilities ratio for a particular firm, its own intrinsic volatility, its size, and many others. And the problem here now becomes, given these economic factors, the common factors as well as the firm specific factors, to estimate the parameters beta and alpha accurately so that one may infer the conditional default probabilities once one observes an out of sample sort of a value of the economic data. And typically, so let me now go and explain what I mean by economic data. So typically, one observes m number of firms. So m is going to be in a few thousands over t time periods, say a few hundred months. And for each firm, I, at a particular time t, so month t, one observes the total covariate. So the VIT is the total covariate observed for firm I at time t, and this is constituted of the global covariate, time t, as well as firm specific covariate for the covariate specific to that particular firm at time t. So you observe this total value of covariate, and you also observe a default indicator. So this is basically telling you whether the firm has defaulted in that particular month or not. And this indicators 1 if the firm defaults, is 0 if it doesn't default. So the total data which you observe is basically tuples of the firm VIT, DIT plus 1 for all firms I and all times t. So for this sort of cross section of firms and also across time, so vertically across time. And the objective now becomes, having seen this enormous amount of data, estimate the parameters beta and alpha accurately. So the beta and alpha, remember, these parameters which were intrinsic to the logic model or to whatever conditional default probability model you assume to be the underlying truth. Now, typically, what one does is one uses maximum likelihood estimation for this. So what you do is you have seen all this data, you assume, say, a logistic model, and you construct the likelihood function of so that basically tells you how likely the parameters beta alpha are given all this economic data, and what you do is maximize it. And the problem with maximum likelihood estimation is, because of the huge amounts of data which are typically used, it is very slow. It takes a lot of time to compute the maximum likelihood estimate. And the second problem of the maximum likelihood estimation is that it's an optimization algorithm, so it's a numerical procedure. So so given data, it'll just spit out certain parameters. And although these parameters are very accurate and they're very close to what the true parameters are if the amount of data is large, they don't. So this procedure does not really give an intuition into how the parameters depend on the underlying data which you have. And this kind of interpretability actually has become a big deal over the past 2 years. So one wishes that the estimators is one develops, so these parameters do have certain kind of interpretability. So one wishes that he knows how these parameter estimates sort of depend on the underlying data. And our contribution is going to be, like I mentioned, to sort of alleviate these two difficulties. So we develop closed form approximates for the maximum likelihood estimation procedure. And by that I mean we estimate the parameters by a function phi, which is explicitly we explicitly can compute the function. So we know the explicit form of the function phi as a function of all the data which is available. And this sort of gets rid of both the difficulties in that, because it's a closed form approximate, it computes estimates instantly. And because it's a closed form approximate, we'll also be able to derive certain structural insights into how these parameters depend on the underlying data. Okay. Now let me the way we derive this is actually rather complicated. And what I'm going to do is I'm going to just give you an intuitive flavor as to how one goes about deriving these closed form approximations. And for that, what I'm going to do is I'm going to assume that the model generating defaults, so the conditional default probabilities, have this logistic form. Okay, and the two underlying parameters are beta, alpha. So these are the true parameters, and you are given all this data, and you want to estimate these parameters from the data. And what one basically does in maximum likelihood estimation is one solves the first order equations, optimality equations, which are associated with the MLE problem. And for the logistic model, these are the equations that you get, and these are kind of complicated. But what one then realizes is that defaults are typically rare because these firms are of higher quality, so they don't default very often. In addition to that, one also realizes that the maximum likelihood estimate is consistent. So as you increase the amount of firms and time periods of data, these parameters, the solutions to these equations become closer and closer to the true underlying parameters. And then one uses certain Taylor series expansions on these equations and certain Gaussian assumptions on the covariates themselves to arrive at the estimate that if defaults are rare and the amount of data available is sufficiently large, the underlying parameters can be approximated by, and I'm going to assume that this is basically, by the way, this is the covariance matrix of the underlying data. The underlying parameters are approximated by the inverse of the covariance matrix times the weighted average of the covariates just before a default occurs. So this is going to be our closed form estimate, right? So this is so the parameters are going to be approximated by the covariance matrix, the inverse of the covariance matrix of the distribution of the underlying covariates times the weighted average of the covariates themselves just before default occurs. And these approximations are basically derived by applying certain asymptotic results to the first order MLE optimality equations. I mentioned a few conditions under which these approximations hold. Firstly, I said that defaults are rare. And secondly, I said that these approximations require that both the number of firms of data as well as the number of time periods of data are large. And in order to quantify the errors incurred by these closed form approximations, so the error between this approximation, the true parameter beta, as a function of the amount of data available and the rarity of defaults, we develop an asymptotic regime in which, as the default probability goes to 0, we quantify very precisely what these errors are. And in the next few slides, what I'm going to do is I'm going to explain what this asymptotic regime is. And then I'm going to show you the main theorem which we have, which quantifies these errors very precisely as a function of the amount of data which we have, as well as our underlying default probabilities. And this asymptotic regime is basically motivated by the fact that defaults are rare. So what we do is we sort of index our problem by the default probability gamma, which goes to 0. And we assume that given the covariates, if the underlying kind of if sort of the parameter of the asymptotic was gamma, the default probabilities are exponentially affine to the first order. So basically e power beta transpose v minus alpha plus a capital O of gamma square term. So they're exponentially affine. Examples that satisfy this property are the logistic model, which we saw before, as well as this default intensity model, where one assumes that defaults are the first arrival times of certain doubly stochastic Poisson processes. So these are Poisson processes whose intensity is stochastic, and it is driven by the covariates. So these models have also been used very widely in practice, and the logistic model which we just saw. So basically, these are two very popularly used models for conditional default probabilities, and both these satisfy this assumption on conditional default probabilities. And I also said that we allow time periods and forms of data to become large. And the way we do this is we basically let T of gamma increase as gamma goes to 0 in this manner. And we let M of gamma increase as gamma goes to 0 in this manner. Typically, what's going to happen is that zeta is something as a number between 0 and 1, because that captures the fact that we have a few hundred months of data. And delta is a number which is between, say, is roughly equal to 1, because we have a few thousand forms of data. And default probabilities are going to be roughly of order 1 in 1,000 per month. And these forms are, by the way, is motivated entirely by practice. So we are trying to capture a realistic setting by assuming this particular structure for the asymptotic regime. So okay, I said a few things. So what I'm going to do is I'm going to recap what the asymptotic regime exactly is before giving you the precise accuracy guarantees. So the first point which I mentioned was that defaults are rare. So we sort of index the problem by the default probability with something proportional to default probability, and that is the factor gamma which goes to 0. Then we assume that given the covariates VIT, economic covariates VIT, the default probabilities are exponentially affine to the first order. So that basically says that the default probabilities are approximately equal to gamma times e power beta transpose VIT. The third assumption which we made was the amount of time periods of data available, which we said was increasing to infinity as gamma goes to 0 in this manner, where zeta just depends on the amount of data which you have, but it's a number between 0 and 1. And the fourth assumption which we made was the number of forms of data which you have also goes to infinity as defaults become rare in this particular manner, and delta is going to be a number which is approximately equal to 1. And under these set of assumptions, our estimate for the underlying parameter is just the inverse of the covariance matrix of the underlying data times the weighted average of the covariates just before the default occurs. So this is the same thing what we saw before. So we have got this nice asymptotic regime. We have this closed form estimate. Now we see a result which is the main result of our paper, which shows how accurate this estimate is as a function of how much data you have and what the default probability is. So the main theorem is as follows. So this quantity is basically the square error between the closed form estimate and the underlying true parameter. And we show that it depends on, it's sort of a sum of two factors. And those two factors are the following. The first term in the sort of asymptotic error is 1 over, the way to read this is 1 over default probability times the number of time periods of data available times the number of forms of data available. So basically this is equal to 1 over the total amount of data. So the cross-sectional data times the forms of data available. So this is the first term in the error. And the second term in the error, and this results basically due to a certain Taylor series expansion which we need to do and then carefully analyze. And then basically results due to some things which don't diversify with increasing number of forms. And this term is just proportional to 1 over the total number of time periods of data which we have. So the total error depends on this guy, which is sort of 1 over probability times total amount of data, plus this guy, which is 1 over the total forms of data, total time periods of data which we have. And this accuracy guarantee is really nice in the sense that it very precisely quantifies the dependence of the error on the default probability and the total amount of data available. And what this is telling, and one insight which one gets from here is how one should gather the data while using our estimator. And that is to say that if the number of forms of data available was reasonably small, increasing the number of forms of data available further does improve the accuracy of the estimator, because this is a term which dominates the error in that setting. But if you had a large number of forms of data, so where the delta which I showed before was larger than 1, then increasing forms of data further does not affect accuracy of the estimator, because then this term starts to dominate, and this is independent of the number of forms of data available. So this result is really nice in the sense that it gives you a very precise quantification of how much data is required to use our estimator accurately. Now, it's also nice because it's telling us that the approximate, so the closed form approximation to the underlying parameters leads to a low error in parameter estimates. So a low error of estimation. And that suggests, and like if you recall, the beta hat which I showed was like the weighted average of covariates just before default. So the beta hat just depends on the value of the covariates just before a default occurs. And because this beta hat was obtained from the MLE by certain first order approximations, one also hopes that the MLE to a large extent depends on the value of covariates just before default occurs. And this is very crucial from a data gathering standpoint, because it is telling us that if the data, so the covariate data just before a default is occurring is accurate, then the errors which one incurs are hopefully not too small while using the MLE, and obviously while using our estimator, because our estimator does not depend on all the previous values anyways. And this is actually very crucial from an implementation standpoint, because if one does take a look at how the US corporate data, for example, looks, there are a large number of covariate values which are missing. And it so turns out that at least in the data which we looked at, these values fortunately do not occur when just before the defaults occur. So the values which are missing are far away from the points at which default is occurring. So basically this gives an idea as to so at what points one must have the financial data, covariate data, to make accurate estimates. So that was what I had to say about our closed form estimator. But there is the MLE, and it is known that the MLE is the best what one can do in parameter estimate. And it is interesting to see how the MLE behaves in the same asymptotic regime. If nothing else, to compare how our estimator works with MLE and whether we can derive competitive ratios and so on. And it turns out that one can derive a central limit theorem for the MLE as well. So the error in estimation, so beta hat m gamma, by the way, is the maximum likelihood estimate error. And this error one can show basically decays is 1 over probability times time periods times forms of data. So this was basically the first term which we saw in the asymptotic error for our estimator. So this precisely quantifies how at the rate at which the MLE error decays, and the limiting kind of covariance matrix here for the normal distribution quantifies the quantifies the constant in the error, sort of the sort of constants which occur together with this decay rate. And because the rate at which the MLE error decays is the same as the rate at which the rate at which the error in the closed form approximation decays, if the number of forms of data available is small, one can conduct a comparison between the performance of the MLE versus the performance of our estimator. And we do that, and we observe that the ratio of the errors between our estimator and the MLE converges to 1 plus the norm of the underlying parameter square as the default event becomes real. So we obtain a very precise quantification for this competitive ratio. And typically this number is not going to be too large. So what this is suggesting is that at least when you have a restricted number of forms of data available, the closed form approximation is quite close to the maximum likelihood estimation in the asymptotic error sense. And by the way, this kind of a maximum this kind of a central limit theorem on MLE itself is new in the rare event setting. So there are central limit theorems for maximum likelihood estimation known when the events are not. So when these default events are not rare, but when they are rare, this is kind of a new result in that setting as well. Now that we have derived the error bounds in maximum likelihood estimation, we have derived the error bounds in our approximation. One wishes to conduct a numerical analysis to see whether these error bounds hold in practical settings, because the error bounds are asymptotic. One wishes to see whether they sort of work in practically relevant settings. And for that we conduct sort of two sets of experiments. In the first set of experiments, what we assume that so we generate defaults using a known underlying model. So the betas we know, and the default model which we use is the forward intensity model, which I showed you before. So we know what the true betas are, and we estimate the betas from the data using our estimate and the MLE. And then we compare the root mean square errors incurred in estimation for both the methods. And we find out that if the number of firms are roughly around 5,000 or less than 5,000, then the closed form estimator does almost as well as the MLE. By almost as well, I mean you basically the error approaches this competitive ratio. And even when the firms are around 10,000 or 12,000, the closed form approximation doesn't do too much worse than the MLE. So then the error is a little bit more, but it's still comparable. And this is despite the fact that the closed form approximation computes things almost instantly. And actually what one can do here is that one can use this closed form approximation as a starting point for the algorithms which are used to numerically solve the MLE. And in fact, this significantly boosts the new MLE sort of speed as well. Okay, so this was with the simulated data where one knows what the underlying model is. But when you do experiments on US corporate data, one does not know what the underlying parameters are, right? Because you're just assuming an underlying default model to be true, and then you're calibrating to this, and you're calibrating parameters. So the way one compares estimators in this regime is by analyzing how well they rank defaults. So how well one is able to rate defaulting firms based on their conditional default probabilities. And it turns out that although the MLE does outperform our estimator, it doesn't outperform the estimator by much. So in terms of performance on real data, the closed form estimator, it's comparable to the MLE. I mean, I would not say it's as good as MLE, but it is still comparable to the MLE in performance on real data as well, in terms of ranking firms in order of, say, default risk. We also do a few other things. So I mentioned missing data. I mentioned how our estimator gives an idea as to how missing data affects the MLE. In fact, what we show is that if the data is noisy, so if there's additive noise in the data, the approximate MLE, so the closed form MLE, still gives an unbiased estimate, and the MLE will incur a bias. And this is in a particular representative setting, but we show a case where the closed form estimator has a better kind of a performance than the MLE. And we also incorporate regularization in this setup. And we observe that for the regularized MLE, the approximation turns out to be the solution of a convex optimization problem. And we derive convergence guarantees for this setting as well. So with that, I come to the end of part 1 of my talk. Before I begin part 2, I just take a few questions, because this is sort of a new kind of a problem.
I could ask a question if this is a good time.
Yeah.
Sure. So the covariance matrix that shows up in your approximation is the covariance matrix of the features, right? That you're using for predicting
Yes.
defaults.
Yes.
One possibility is that the covariance features have a different covariance for the defaulters than for the non-defaulters. So that ultimately there are sort of two different covariance matrices. Have you thought at all about how your analysis might extend to a situation like that?
Yeah, that's actually that is actually a very interesting question. I've not actually thought about this, no. But yeah, I mean, the way one would approach this is to basically write down the first order equations, but now with replacing the kind of the defaulters covariance matrix by something different. So whenever you see a default, you just the statistics of the data change there, and then try and apply these law of large number approximations. But I think so long as you assume these Gaussian sort of conditions, it should go through. Only thing you'll get some maybe hybrid sort of a closed form estimate. I mean, you may not get the C inverse, you might get something else, but I suspect you will get something close form because you're assuming underlying covariance are Gaussian. If they're not Gaussian, then of course these law of large number approximations don't really work out. So then in that setting, I really cannot say much. But if you assume that the defaulting the covariates at the time, the covariates have at the time of default are also Gaussian, then you might end up getting close form approximations, but something different from what we have.
Right. And if you didn't make the gamma going to zero assumption of rare defaults, and you just assumed that the covariates are Gaussian,
yes,
I mean, how close do you get to the same approximation for beta?
Yeah. So so if you don't assume the events are defaults are rare, in fact, one will not get the correct approximation. So let me just go back a little bit, and I will explain why. So yeah, let's look at these equations, right? So the way we arrive at our approximation is basically by approximating this quantity by one, and that requires that the defaults are rare. So that's what I mean by gamma going to zero. And then you apply a law of large numbers. So this is basically you calculate moments of Gaussians and you calculate exponential moments of Gaussians and arrive at the estimates. And approximating this guy by something like v times e power something, that requires that this denominator is typically small, and that requires gamma going to zero. So if you did not if you assume that the defaults are not rare, then you may not end up getting close form approximations. I mean, you won't end up getting this nice ratio representation.
Thanks.
So, okay. So with that, I will go to the second part of the talk. And that concerns estimation and analysis and estimation of certain tail risks. And like I mentioned, this is joint work with Karthik and it has appeared in a variety of venues. And this section broadly consists of solving two problems. And the first one, what we do is we estimate certain tail probabilities. So we derive accurate algorithms to estimate certain tail probabilities. And these algorithms have found widespread practice, widespread use in like a variety of settings, like I mentioned, in financial risk analysis, in the insurance setting, in analysis of network delays, as well as in more machine learning based sort of a machine learning kind of areas more recently. The second problem which we solve is, like I mentioned before, how to incorporate how one incorporates the presence of tail risks into an optimization framework to make decisions which are sort of tail risk aware. And this is a problem which has actually, I mean, has been studied widely in portfolio optimization over the last 2 decades, and as well as in power networks. And this is a difficult problem because, like, to make tail constraint decisions, one usually requires a very large amount of data, but one is normally restricted by the amount of data which is available through nature. And therefore, if one does try and make these tail constraint decisions, these decisions are usually very fragile to they are not very robust. And so this has been a challenging problem for the past few years, and we derive low data kind of and accurate kind of methods to solve this problem. So we solve this problem with practical amounts of data, basically. The third thing which I present in the thesis, but I won't talk about today, is how one uses these approximations, and one uses this tail risk analysis to derive certain structural insights into occurrence of rare events. And again, this is found widespread applications in finance. But due to the lack of time, I won't be discussing this in today's talk, and I will be restricting myself to estimation of tail risks. So both in estimation of probability setting as well as in the optimization setting, in the data-driven optimization setting. Just to recap, we consider three things in the thesis, but I will talk about only these two, and that is estimation of rare event probabilities and also optimization with sort of a tail risk kind of with tail risk sensitive optimization essentially. So the first part, like I mentioned, will be to simulate probabilities in a computationally tractable manner, rare event probabilities in a computationally tractable manner. And the problem which we are going to deal with is the following. So we are going to assume that there is some objective loss L, and given certain factors, zeta, stochastic factors zeta, the loss incurred by a system of interest is L of zeta. And our objective is going to be to derive an algorithm to accurately estimate the probability P of L of zeta greater than U, where U is a large number and U is basically usually denotes some kind of safety or reliability constraints which the system must satisfy. So we want to estimate these kind of probabilities accurately. And the kind of losses which we want to deal with are rather general, and I would like to motivate with the use of two examples. So one is the shortest path problem, which is kind of a mixed integer linear program. And the problem is as follows: if you have a random graph and you want to sort of go, if you have a graph and you want to go from source to a destination, and transversing along each of these edges has a particular cost. The problem involves finding the least cost of transversal from source to destination. But in our case, what we are going to assume is that the delays, so the costs of travel along these edges, are stochastic. So the zeta corresponds to these transversal costs. And then basically what happens is that the least cost of traveling from source to destination becomes a random variable whose value depends on the realized value of zeta. And naturally, because the underlying graphs can be complicated, so these paths can be complicated, this is kind of an intractable object. So there is no closed form kind of solution to this. The second kind of loss which I would like to motivate by is a more machine learning kind of a problem, where we deal with outputs of neural networks. And in neural networks, and so basically the loss here is the output of certain neural network which has been trained to some historical data. And neural networks themselves are very complicated, so they consist of many hidden layers. And so this loss as a function of the underlying covariates cannot be explicitly identified. I mean, the functional form of this loss cannot be usually explicitly identified. And well, we don't actually just restrict ourselves to these two losses, but a more general category which just includes these two. And the assumption which we are going to make on L and the underlying covariate zeta is the following. So we're going to assume that the underlying loss satisfies a tail regularity condition. And I would like you to think of this tail regularity condition as saying the loss is a multivariate polynomial. So that is all this condition is saying. It's rather technical in nature, but it's basically saying the loss is a multivariate polynomial, and it's not just any polynomial, it's a homogeneous polynomial of order rho for some positive rho. And we're also going to assume that the density, so the underlying density, the density of the underlying covariate satisfies this exponentially regular condition. So the e power psi of x, where psi of x has got some tail regularity. And again, the way I would like you to think of this is that the psi of x is a multivariate polynomial, which now need not be rho homogeneous, but it is still a polynomial. What I would like to emphasize here is that this captures a very general set of losses as well as a very general set of covariates. And we want to sort of estimate the rare event probabilities for L of zeta greater than U for this in this generality. And well, some examples of losses and covariates which satisfy this condition are the two which I showed you before. So the shortest path problem actually has L star x, which is very easily representable by this form. And the neural network has a L star x, which is representable by something slightly more complicated. So the phi star depends on basically the neural network which has been trained, but basically these two losses still satisfy this tail regularity assumption on the tail regularity assumption. The zeta density also was something which is very complicated. And what I would like to convince you in the next few slides is that it is satisfied, that very complicated technical condition is satisfied for most kind of covariate distributions which one would deal with. So that includes, for example, elliptical densities. So what I do here is I list down the elliptical density and the limiting psi star, which occurs in the assumption. It is also satisfied by log concave densities. So this kind of a setting. And exponential families, so this kind of a setting, and mixtures of these guys, and many other cases which we deal with in our paper as well as in my thesis. So if you sort of want to see what all L's and what all Zetas are covered by these assumptions, I would encourage you to look at either of the two. But the point is that the assumption which I'm stating is very general, and we want to simulate rare event probabilities for this very general class of problems. Well, actually, okay, so right, so so this actually has found widespread. So rare event simulation has been around for a long time, and the way one typically does this is via the use of importance sampling, which I will outline next. And remember, the objective was to estimate P of L of zeta greater than or equal to U. So the probability that the loss exceeds the threshold U. And one very naive way of doing this is to just draw samples of zeta, independent samples of zeta, n number of them, to find out whether for each of these samples the loss exceeds U, and this just to return the average number of so just to return the fraction of cases in which this occurs as the estimate for the probability. And this is a consistent estimator. So in that, if I increase the number of samples to infinity, this will converge to the true probability which I'm trying to estimate. But the problem is that typically, since I'm dealing with safety constraints and I'm dealing with reliability issues, the U is going to be something which is large, and these probabilities are going to be small. So the probability of seeing any one of these indicators to be positive is going to be something very small. And the amount of computation therefore required to estimate this probability accurately using the naive estimator is prohibitively large. So instead of doing this naive sort of Monte Carlo, one resorts to other methods, and importance sampling is one other very powerful method which one can use. And the way importance sampling works is that one says that, okay, I will not sample from the distribution of zeta because the event of interest is very rare under the distribution of zeta, but I will sample from something else, some other distribution under which the event of interest is much more common. And because sampling from an alternate distribution results in a biased estimator, I will carefully debias the estimator by a likelihood ratio in order to restore consistency. Mathematically, this means the following. So we are trying to estimate P of L of zeta greater than U. What one will do is write this down as sort of the integral of the density over the region of interest. And then what one does is take change of measure. So you multiply and divide by a density G. And then you realize that this quantity is actually equal to the expectation under the new distribution. So the big G has a density little g. So the expectation on the new distribution of this likelihood, so the ratio of the densities times the indicator that the event occurs. And this provides an alternate estimator for the rare event. In that, what one can do is one can draw samples from G instead, so n samples from G instead, and return this quantity as an estimator. And again, because of the law of large numbers, this will be consistent, and more so by the central limit theorem. So A here is basically the set L of zeta greater than U. By the central limit theorem, the error in this estimation will depend on the variance, the sample variance of the importance sampling this estimator under the alternate distribution G. So sigma IS is just the variance of the importance sampling estimator under the alternate distribution. And so long as one can control this, one can choose an alternate distribution G where one can control this variance and keep it small, one can obtain a reduction in sample complexity required to estimate these rare event probabilities. So the game is basically to sort of obtain low variance estimates, low variance importance sampling estimators. And this, like I mentioned, importance sampling has been around for a long time, and it has received a lot of attention in quantitative finance, in network analysis, in delay analysis, and a lot of other fields, and more recently in machine learning. But what is typically done, and remember, here I would like to stress that we want to deal with a very general category of losses and a very general category of covariates. And that is why a sort of algorithms which have been used in practice, and these algorithms actually work very well for the problem they're designed to solve, we cannot adapt them to our method. And the reason being that these algorithms are typically designed keeping a particular problem and covariate structure in mind, whereas we want to work in a very general setting. So we want to work, for example, with machine learning losses or these complicated optimization problems and so on. But I mean, whatever work has been done does motivate the way we will approach the problem. And the way we approach the problem is the following. Step one will be to establish a tail asymptotic. So what we do is, we establish an asymptotic for the probability that L of zeta greater than U as U becomes large. So this provides certain structural insights into how the rare event occurs. This provides us insight into what the concentration properties are when the rare event occurs. And step 2 will be to use these kind of insights, these concentration insights into how the concentration of measure occurs when the rare event happens, to obtain the alternate distribution. And actually, this is basically what one does when one designs an importance sampling distribution. One derives tail asymptotics, and using the structural insights from those tail asymptotics, one derives an alternate importance sampling distribution. Okay, so like I would like to sort of restate that we are doing this under a very general set of conditions. So our first contribution is that for this very general set of conditions, we derive a tail asymptotic. So that was the step. That was step 1, which I said. So derive a tail asymptotic for P of L of zeta greater than or equal to U. And this tail asymptotic by itself provides certain structural insights. I mentioned that briefly in the introduction to the section, and I will not discuss those further. But it provides certain structural insights which are useful for design. But for us, we are more looking at computational issues. So we use, in designing the importance sampling, in design of efficient computation algorithms, the main insight which this tail asymptotic gives you is a notion of self-similarity. And to introduce the notion of self-similarity, let me consider a very simple example where the loss is just a two-dimensional. I'm going to consider a two-dimensional example where the loss is just the sum of the two individual components. And above in red is the conditional distribution of the covariates, given that the loss is larger than level 15, so U equal to 15. And below is the conditional distribution of the covariates, given that the loss exceeds a smaller level, 10. And if you notice, these two distributions concentrate about a similar set of points. And this is the notion of self-similarity which you isolate, in that if one were to consider if one were to consider how the event L of zeta greater than U happens, one could infer it from the event L of zeta greater than or equal to L, because events which happen in the tail are structurally similar in nature under the set of assumptions which I showed you. And the structurally similar, by structurally similar I mean one can be recovered from the others. One can be kind of recovered from the other modulo a carefully designed scaling. So again, what one does is, in order to infer the target rare event, so how the target rare event happens, so L of zeta greater than U, what one does is one uses a structurally representative but less rare event to infer how this kind of measure concentration happens at the sort of the target event. And the design of the importance sampling estimator is basically based on drawing such inferences. So how do we do this? Well, we do this via a sort of a extrapolation map. So what we do is that we identify a map T, okay, which takes the structural features learned at the lower level. So what I mean by that is it infers the concentration properties at a lower but less, so a structurally representative but less rare level. And it uses these concentration properties to kind of learn what the how this measure is sort of concentrating in the event of interest. And what we do basically is we use T of zeta as importance sampling distribution, and T, as you will see, is a very simple function. So if you can sample from zeta, you can easily sample from T of zeta. And by learning sort of structural properties of the more rare event from less rare events, we incur a significant reduction in the amount of computation required to estimate these rare probabilities. Now, okay, so basically this is what's happening. So what we do is, so what the map T is doing is, it's taking the blue points which, remember, were here, and it's sort of stretching them out in a way which respects the large deviation asymptotic. And the map T doesn't need to know the large deviation asymptotic. Is designed so that it is designed so that it implicitly respects the large deviation asymptotic. And having respected the large deviation asymptotic, what it's doing is it's mapping the blue points which were here, which are representative of sort of the lower level event, to the target event. So the sort of concentration properties of a very rare event are learned from those of a less rare event, but a structurally representative event. Roughly speaking, this is what's happening. What the map T is doing, I will show you what precisely the map is, but what the map T is doing is it's taking points from the region L of x greater than or equal to L, where L is some number less than U. So these are points which are rare, but are less rare than the target event. So it is possible to see such points with a reasonable amount of computation, and is taking these points in an appropriate way and is mapping them to the target region. So it's sort of mapping them to the target region L of x greater than or equal to u. And in doing so, it's sort of learning these concentration profiles from less rare samples. And because we only need to now know how these points occur, so the lower level points occur, the computation required to sort of estimate these probabilities now just depends on how much computation is required to estimate this event. And because L is going to be chosen to be order of magnitude less than u, this is significantly smaller than what would be required just using naive Monte Carlo. I will now come to the map T. So the map T basically involves taking a point x. So T of x basically involves taking a point x and stretching the point out depending on how the magnitude of the individual components look like. So if you look at the form here, so the kappa of x is the exponentiation factor. So u by L per kappa of x determines how much a point is stretched. And if you look at the form of kappa of x, two things are apparent. Number one, if a point x has, if the ith component of x is large, then the kappa of x will also be large. And so what will happen is that this point x is basically stretched out by a factor of u by L. So the rho, I should just tell you to think of rho as 1 in this setting. So rho was the same thing which appeared in the loss assumption, but for this discussion, you can think of rho to be equal to 1. And what one can do is, so here what's happening is that if the particular point was large, it's being stretched by a factor of u by L. If the point is small, then the kappa of x is roughly equal to 0 because this log of 1 plus the small thing will be small as compared to the denominator, and so the point is not stretched out at all. And it is this kind of a thing that is allowing us to sort of infer more rare events from structurally representative but less rare events. And how is that? Well, I mentioned that the way in which the very rare event happens is structurally similar to the way in which the less rare event happens. So if for the less rare event, say one of the components, both the components were large, so if the blue points were concentrated somewhere here, say, what the kappa would do is it would stretch out both the components, and we know that both the events are sort of structurally similar, so one would obtain an approximation for the target kind of rare event. Similarly, if the event happened, if the rare event happened in a way that only one of the components was large, the kappa would stretch out that particular component but not the other to the target level, and then one would still obtain sort of a match for the conditional distribution which one sought out to approximate. And that is sort of corroborated by the histograms of kappa, which sort of concentrate at the points 1, 0 and 0, 1 when only one of the covariates being large is causing the rare event, which is to say that only one of the components is being stretched out. And sort of these histograms sort of concentrate about 1, 1 when both the components become large. So this is to say that the kappa is sort of stretching out, so the extrapolation is sort of stretching out both the components, and thereby it's sort of maintaining it's learning sort of concentration profiles from events which are less rare but structurally representative. And the accuracy guarantees which we obtain under this kind of an using our kind of algorithm are asymptotic optimality. And asymptotic optimality, I won't get into the technical details, but it basically tells us that if you want to obtain a small relative error in estimation of probabilities, so the probability is PU, instead of requiring order PU inverse samples, which the naive Monte Carlo would require, you require order PU power minus epsilon samples. So you can think of this PU power minus epsilon as basically log of 1 over PU. So the computational complexity has been reduced to 1 over PU to log of 1 over PU. So this is like a drastic computational complexity reduction. Now these results are asymptotic. So as U goes to infinity, so it is useful to see whether they actually work in a practical setting. And for that, we consider the shortest path problem in the numerical implementation, and we basically plot the probability which you're trying to estimate against the log of the variance of the importance sampling estimator. And basically the sample complexity is going to be proportional to the variance of the IS estimator over the probability square. And what this is suggesting is the following. If you were trying to estimate a probability of order, say 10 power minus 6, over the naive sample, over the sort of naive Monte Carlo method, the importance sampling estimator in this case is giving a computational reduction of by a factor of 10 power 4. Therefore, in order to estimate probabilities of 10 power minus 6, instead of requiring a few million samples, one would require only a few hundred. So this is basically signifying a large degree of computational reduction. So basically, actually, in this example, I used n equal to 500. So I used 500 samples to estimate probabilities of order 10 power minus 6. So that's sort of consistent with what one expects in theory as well. So with that, I will come to the end of this section. So where we use simulation to estimate certain rare event probabilities. And I will go into the data-driven optimization framework. I highlight data-driven because the key difference between this part and what we discussed previously is going to be that.
Anand, 1 second.
Yeah.
Let me just check with the Prahlad here. What time frame are we looking at for this talk? When do we want Anand to finish by?
The talk is an hour, followed by questions, and then there'll be a closed door session with Anand, the committee, and other interested faculty. Yes.
So Anand, your hour will end in about 5 minutes, but maybe you can take a total of 10 minutes and wrap up in 10 minutes.
Sure. Okay. So because of lack of time, what I'm going to do is I'm going to run through this really quickly. So here we consider a data-driven kind of a setting where one incorporates tail risk measures into an optimization framework, and the kind of tail risk measures one incorporates are basically conditional value at risk. And I would like you to think of conditional value at risk as basically the worst case average over t fraction of the average of a particular loss over the worst t fraction of outcomes of that loss. So t is a number which is like typically 10 power minus 2 or 10 power minus 3. And here what we consider the following example. So this is a CVAR constraint optimization problem where one minimizes the average loss plus the CVAR of the loss evaluated at a decision parameter x. And in this case, we are going to do a data-driven optimization. So we don't have access to a sampler which one can keep on drawing samples from, but instead we are given certain say financial data, say 1,000 samples, and we have to work with that. And the problem here is that one can implement gradient descents on these kind of problems numerically, like using sample average approximations. But because you are dealing with tail expectations, these sample average approximations are not very accurate. And with the limited amount of data which one has, one typically has they are not very robust, and there are works which show this lack of robustness, and they show that in order to make such inferences at even reasonable levels, you require a huge number of samples, and these many samples of data you will simply do not have access to. And remember, because it's a data-driven framework, one cannot really draw any more samples. You just work with what you have. And here we again work with a tail assumption on the covariate zeta. In this case, we work with a heavy tail assumption. Multivariate Pareto and multivariate T distributions, for example, satisfy this. And okay, so in order to solve these kind of problems, in order to implement this kind of gradient descent, one needs to be able to estimate the gradient of the CVAR accurately. Okay, so our main result is sort of a low data requirement estimator for the gradient of CVAR, and we use this to sort of solve the optimization problem. So what we'll do is we'll plug in our estimator for the CVAR gradient instead of this guy, and we will obtain accurate solutions even with a restricted amount of data. And basically the main theorem is this approximation theorem for the gradient of CVAR, which says that the gradient of the CVAR at the target level, so at a very rare quantile, can be approximated by the gradient of CVAR at a less rare quantile modulo extrapolation. And this is in similar flavor to what we saw before. More rare events can be approximated by less rare events modulo extrapolations. So structurally, because these are structurally similar. And what this is saying is that CVAR gradient at a level 100 can be approximated by CVAR gradient at level 1 in 10. And therefore, instead of requiring sort of order 100 samples to do the computation, you can do it in order 10. So you gain a data requirement, a reduction in the data requirement by a factor of T0 by T if you use these kind of extrapolations. And we sort of incorporate this into a sort of a data-driven estimate for CVAR gradient, and we use this data-driven estimate in solving this risk constraint optimization, which I showed you before. And now, instead of incurring enormous relative errors with practical amount of data, what we observe is that the relative errors in solution are quite small. So what this is telling is that if you wanted to solve this tail constraint optimization problem reasonably deep in the tail, so at quantiles of 1 in 200, the method which we provide kind of does it gives you an accurate relative error of 15% with 400 samples, while if you wanted to obtain the same relative error using conventional sample average methods, you would take around 2,500 samples. So I don't, so this you require around 2,500 samples for it. So you obtain a data requirement by factor of 6, which is a big deal because typically the amount of data which you will have in this setting only is a few thousand samples. So we obtain a significant data reduction. I will very quickly, Sandeep, how much time do I have left?
Maybe 5 minutes.
Oh, okay, so sure. Okay. All right, so I will very quickly run you through the third part, and that concerns with developing limiting approximations of banking networks. Like I mentioned, these banking networks are often complicated, and one wishes to analyze, one wishes to derive certain structural simplifications for them as the network size goes to infinity. And so as I also mentioned, these banks engage in borrowing and lending among each other, and that can be captured using this nice graphical model where a bank is connected to a number of creditors and debtors. It incurs internal operating costs, and it has an external profit which it receives from its loans or some external projects. And this profit is sort of stochastic because these loans can default or the project can go bad, and it can suffer. It can basically receive less income than it expects. And because it receives less income than it expects, what could happen is that instead of being able to pay back its debtors, it cannot pay back its debtors in full. Like these are banks from which it has borrowed money. And because it cannot pay back its debtors in full, the debtor may have a cash shortfall, and it may not be able to pay back its debtors in full. And this distress could kind of propagate to the network and cause a large number of banks in the network to fail. And one can show that this kind of a propagation, this kind of a default cascade can be captured to the fixed point of an n-dimensional operator. So n is the number of banks in the economy, and one can compute this, and one can derive certain, one can infer certain properties of the network from this fixed point. But there are two shortcomings here, in that when you compute these deterministic kind of fixed points, you assume that the modeler has modeler has complete access to the network information. But this is typically not the case, because you'll only have aggregate sort of information. So you'll have statistical information on what the average connectivity of a particular bank is. You might have statistical information on how frequently the bank how frequently the customers of a bank default on this loan. So what the distribution of its external wealth is, but you won't have a precise access to precise realizations of these quantities. And therefore, what we do in order to capture this stochasticity is instead model the network as a random graph. More precisely, we model the network as an Erdős-Renyi graph. And what we do is that we assume that we have access to sort of very granular statistical data on these on this network. So like how many banks a particular bank is connected to on average, what the statistical property of its external assets are, what the statistical properties of its internal operating costs are, and so on. And in this setting, what we show is that firstly, the wealths of a bank satisfy a fixed point equation, but now in the distributional sense. So the distribution of the wealths of the bank in the large network is the fixed point of a sort of a distributional equation. And this equation is rather complicated. So what we further show is that as the number of banks in the network becomes large, this distributional fixed point kind of decouples to give a very nice one-dimensional kind of a product form in the asymptote. So the one-dimensional product form is another distributional fixed point, but now it is a fixed point of a much simpler map T, which essentially depends on the statistics of the underlying network. The only problem here is that in order to draw any inferences, one must be able to compute what T is, but T is not available in closed form. So the fixed point of T is not available in closed form. So in order to compute this fixed point, one must derive a Monte Carlo method, which basically works by approximating the. So if you knew what T was, you would basically keep on hitting T. You start with the distribution lambda naught, and you keep on hitting it with T, and you would arrive at the fixed point. What our approximation does is it basically approximates each of these steps using empirical samples, and we show that we basically show to achieve a particular level of accuracy. So in terms of Wasserstein distance, so this is a metric which kind of quantifies how close two distributions are. We show precisely the number of samples which one must draw to approximate this fixed point, as well as the number of iterations for which one must run this sort of fixed point iteration. And using this, we kind of infer some very basic statistical, so some very basic properties of the network, structural properties of the network in numerical experiments. So here is the set of papers which this thesis and this talk was based on. The first one has appeared in Operations Research. The second sort of set of papers is with Karthik, and so these are the 3 papers on which this talk is based on. And the third one has appeared in Winter Simulation Conference and is based on sort of computing these distribution fixed points. With that, I would thank you for attending. Thank you very much.
So Prahlad, although I intervened, you're the chair of the meeting, right?
No, you are the chair, Sandeep. You're the
I'm the
chair.
chair.
Yeah.
Okay.
I'm.
Okay, so then as a chair, I'll add a comment which I did earlier that, along with being a budding, promising researcher, Anand is also a top quality musician. He's a wonderful pianist. So many of you know this, but if some of you don't, that's something to listen to at some point with Anand. I'll also take this opportunity to thank Professor Glasserman for being in this committee. Paul and I go back to a long time ago. I was in my first year of PhD. After my first year of PhD, I was doing summer internship at Bell Labs, and Paul was a young dynamic researcher then. And we looked at him in a wide-eyed manner. And I think that structure has continued. So he's still a young dynamic researcher, and I still look in a wide-eyed manner to much of the research that he does. So thank you, Paul, for being here. Now the question to everybody in the audience, any questions for Anand?
Yeah, hi Anand. This is Siddharth. Hey. So you'd mentioned this optimality of your this tails rare event simulation
important sampling.
Important sampling thing. So what is that? Could you say a line or two about?
Okay, so asymptotic optimality. So asymptotic optimality is sort of a criteria which one judges how good an importance sampling estimator is by. What it basically tells you is the following. Okay, if you use just naive Monte Carlo, so if you were to just draw samples and try and estimate a probability, so the variance of each of these samples would be of order p.
Okay.
Right. So you would require 1 over p number of samples to do this estimation accurately. What asymptotic optimality is telling you is like if you have an asymptotically optimal importance sampling estimator, so like an alternate distribution, the variance of each of these samples looks like p power 2 times a term which is smaller than polynomial in p. So instead of now requiring 1 over p samples, you would require p power minus epsilon samples, like what I showed you. So like you can think of the p power minus epsilon like a log p samples. So that quantifies the amount of kind of sample reduction which one expects to get when one is using these estimators.
Okay. Okay, thanks.
Any other questions from the audience? So if there are no more questions, I'll request the audience to leave, and the committee will then examine Anand after that. Thank you everyone for coming.